Hello, this is Farhad Hafez from the ELSA Institute in Dietikon, Zurich. I would like to thank the organizers for giving me the opportunity to talk about corneal cross-linking. These are my financial interests. Now, if we look into the past, the idea of cross-linking was born in Germany, but the entire implementation into clinical practice happened in Zurich, Switzerland. We were a team of 4 doctors, as you can see in the upper left, around Theo Seiler. And this is the technology that we created in 2003. This was the first cross-linking device. You see in the upper right the very first publication about the concept from 1997. Now, ever since, cross-linking has gone a long way. And nowadays it is a global standard of care in the treatment of keratoconus. It has a CE mark, FDA approval. We estimate roughly 200,000 procedures a year, and you will find more than 2,000 publications in Medline. But what makes me personally very proud is that since the introduction of cross-linking, the number of keratoplasties has dropped by 50% in countries that have a central registry. A few years after the first indication of keratoconus, we observed that the combination of UV light and riboflavin also works very well in infections of the cornea, and we published the first paper back in 2008. A few years later, Brett Wendelman and I coined the term PAC cross-linking, which stands for photoactivated chromophore for keratitis cross-linking. Ever since, in 2010, I became chairman of the University Hospital of Geneva, Switzerland, and my research group to date has published roughly 5% of the global output on the scientific literature regarding corneal cross-linking. What we have been focusing was to improve the technology and make it more user-friendly. Now let's go to the present. One important step to make it more user-friendly would be to omit the step of removing the epithelium. So instead of removing the epithelium, leaving the epithelium on, which we call epi-on cross-linking. Now, epi-on cross-linking took more than 10 years to be developed. It was really hard because in the beginning, in the early days of cross-linking, we only thought of 2 factors that should influence the reaction, which are UV light and riboflavin. What we did not know back in 2009, 10 and 11 is that oxygen is an essential additional element, and diffusion of oxygen plays a central role in the efficacy of the reaction. The fact that oxygen is central was only discovered in 2013 and 14. This was my research group. In 2013, we did cross-linking in the absence of oxygen, and then we observed 0 increase in biomechanics. 1 year later, we showed that the famous Dresden protocol, which is the most widely used protocol in epi-off cross-linking, this is the blue bar, creates a strong increase in biomechanics. But even if you accelerate gently from 30 minutes to 10 minutes, you already lose efficacy. Now the red bar, that's 9 milliwatts for 10 minutes, is used very often in clinical practice, but it is less stable biomechanically than the 30 minutes protocol. And this is why in many cases where we are facing a very aggressive form of keratoconus, like keratoconus in children, many colleagues, including me, went back to the Dresden protocol because it gives us the strongest biomechanics. Now let me show you why this is not necessary anymore. And I prepared the following slide for a long time because it took me time to understand how to make this easy to understand and how to explain this the correct way. The reason why we have so many different protocols nowadays for cross-linking is because there are so many factors that play into the reaction, like the ones you see here. Now, let's have a look at epi-off cross-linking, and I will try to explain all the developments of the last years in one single slide. Now, what you see here is for every cross-linking reaction, you need UVA light, oxygen and riboflavin. Now, I assume that you have a well-functioning lamp, so you always have enough UVA, right? The question is, do you have enough oxygen and do you have enough riboflavin in your reaction? And the success of a cross-linking reaction would be 0 here on the left and 100% on the right. Now let's start with the first protocol that was established, which is the famous Dresden protocol. 30 minutes at 3 milliwatts per square centimeter. And if you multiply these two, 30 minutes is 1,800 seconds times 3 milliwatts is 5,400 millijoule or 5.4 joule. That's the total energy. If you do this, and this was the case in 2008, then you will see a very strong reaction. Now, a few years later, around 2008, industry came up with the idea we could accelerate the treatment if we go down with time, but in the same instance, we go up with intensity. So instead of 30 minutes, we do 10 minutes with 3 times the energy, because the end product still is 5.4 joule. Now, by doing so, let's have a look what happens here with the success rate. As you can see here, the success rate, if you accelerate slightly, is still good, but goes down. Why does it go down? It goes down because if you go a little faster, then oxygen, which is essential for the reaction, has a harder time being present in enough high quantities. It simply takes time to rediffuse, and if you make the reaction too fast, then you lose a little bit of oxygen availability. Still enough oxygen, but less. Now you can imagine what happens if you go even faster. Look at the right side. We go down to 5 minutes and we compensate with the intensity, so the fluence still is the same. What happens to the cross-linking success? That's a mixed bag. It's undecisive. And that's the 5 minutes protocol. It sometimes works, it sometimes doesn't. Why? Because you have even less riboflavin. And this is epi-off cross-linking. We talk about 2010 now. If you try to go even faster, and this was the case 10 years ago, if you go down to from 5 to 3 minutes, and you compensate with intensity, then the success rate is really bad. Too fast, no more oxygen present in that cornea. The light is still okay, and riboflavin is okay because we did an epi-off procedure, so a riboflavin can easily penetrate. This was 2010. Now, if we look at the original Dresden protocol, which is still the strongest, the question was, is there any other protocol we could establish that is faster but still keeps the same biomechanical stability? And the good answer is there finally is such a protocol. We developed such a protocol by speeding up the process by roughly a factor 3 and by increasing the intensity not by 3 but by 6, by a factor 6. Look what happens here. We go down to 9 minutes 15 at 18 milliwatts, which is a total of 10 joule, not 5.4. And the efficacy is just as good as the Dresden protocol. We have published this in TVST, the ARVO journal, end of last year, and we are now in the clinical validation phase. So I'm really confident that very soon we can give you an epi-off cross-linking protocol 3 times faster than Dresden with the same efficacy. But the real holy grail is epi-on cross-linking. And in epi-on, we have more factors to overcome because the epithelium is a blocker to oxygen and a blocker to riboflavin. So epi-on cross-linking started 13 years ago with an Italian group that simply said, let's do the Dresden protocol. We simply don't remove the epithelium. Well, if you do this, that's a bad idea. The success is very bad. And this is why 5 years later, another Italian group invented the use of iontophoresis. So an active transport of riboflavin into the cornea. By applying iontophoresis, they were able to improve on the success rate. As you can see here, it's a little better. Because they have more riboflavin available. Why is it not better? Well, because you still have not taken care of the oxygen, just of the riboflavin. The next idea was to pulse the light on, light off. The idea was to let oxygen rediffuse during the off period. This again, pulsed light, again look at the CXL success in the upper left. It improved a little bit only because in fact you cannot do 1 second on and 1 second off. Physiologically you have to do 1 second on and 2 minutes off, which doesn't make any sense. So again, oxygen availability was a little bit better, but not good enough. And lastly, some other industry had the idea of giving oxygen goggles to the patients, pure oxygen around the eye. So instead of 21% of oxygen we have around us, 100% oxygen. And then the success rate is much better because you have much more oxygen at disposition. So this works, but I still don't like it too much. Why? Because during my entire career, my idea was to simplify the method and not make it more complex. So now you can do epi-on cross-linking, which is very good, low infection risk, fast rehabilitation, but you need a cross-linking device, a iontophoresis device, an oxygen tank, and oxygen goggles. Now the question was, is there a way we could not use 100% oxygen, but just the 21% oxygen? And the answer was yes. This is what a friend of us, Cosimo Mazzotta, managed in 2020. And he did, look here, he did an intelligent combination of factors by pulsing the light, gentle acceleration, high intensity, pulsed light, 7 joule, and iontophoresis. And then he had good success. So this is already much better. He published 3-year follow-up clinical data. I like this much better, but now the question was, maybe we can also get rid of the iontophoresis. And indeed we can. How? And this is epi-on, the way we established this at the ELSA Institute in 2021, by using what we call second-generation penetration enhancers. This took us almost 1.5 years. Besides being a refractive surgeon, I spent my past 30 years also in ocular cell biology. So we went to the multiphoton microscope at the Swiss Federal Institute of Technology almost every Thursday for a year, and we tried to find a way to improve the penetration through the epithelium so that it becomes similar to iontophoresis. And finally, we managed. So now we have epi-on cross-linking without additional oxygen, without iontophoresis. So this is the present. Another really exciting element is that we are able to overcome the limit of 400 micron in keratoconus corneas. A dream would be to even be able to cross-link a very advanced keratoconus cornea like this one, 215 micron. Now, if you look at what has been proposed in the past 20 years as protocols for thin corneas, then the first one came from our group. We introduced hypoosmolaric riboflavin in 2009, which means swelling of the cornea. And a few years later, Susan Jacob introduced contact lens assisted cross-linking. Both methods have major disadvantages, and I don't use them anymore. Our own method has the disadvantage of being unpredictable in the amount of swelling. The biomechanics is really good. This has been published, even if the cornea is swollen. But sometimes the cornea swells a lot, sometimes it just doesn't swell. So you have a surprise ahead of you, which is never a good feeling. And in the case of contact lens assisted cross-linking, the idea is really good, but the best contact lens in the world blocks a part of oxygen diffusion, and you lose 1/3 of the efficacy. So not a good idea either. But if you think about these two concepts, both concepts artificially increase corneal thickness. So basically we have a method and the human doesn't fit our method. So we modify the human cornea to fit our method. Adapt the cornea to my technique. That doesn't really make sense. What makes much more sense is instead of adapting the cornea to the technique, we should adapt the technique to the cornea. If you have a cataract patient with a very hard nucleus and your cataract machine is set to clear lens extraction with very low power, you will not send the patient home. You will adapt your machine settings, right? So it makes much more sense. And this is what we call individualized crosslinking, the sub 400 protocol. We developed an algorithm and published it 5 years ago, which adapts the fluence according to the thickness of the patient's individual cornea. We published this algorithm, and then we went into a clinical validation study, and now we have standardized steps. You perform an abrasion, you apply riboflavin. After 10 minutes, you measure the thickness with the pachymetry, ultrasound pachymetry, and then you take this thickness, and according to the thickness, you adapt the fluence. We've published the follow-up data in the American Journal of Ophthalmology, and it works like a charm. So you have a table where you exactly see how many minutes you have to apply according to the patient's individual thickness. And these are the data we published. A surprising success rate of 89%. We will publish the 2-year follow-up data now in a follow-up study, and we are at 82%, so still remarkably high. We speak about corneas of 210, 220 microns, extremely thin corneas. This protocol is so successful that we were the first being able to crosslink even keratoglobus. And of course, this only makes sense if you can crosslink a cornea that still gives you useful vision. And we know that nowadays, modern scleral lenses can do miracles in improving vision. By the way, you can use this sub 400 protocol and the table with any crosslinking machine, but in the case of the slit lamp crosslinking, which I developed, the algorithm is integrated into the machine. So in conclusion, the future in ultra-thin corneas is individualized crosslinking. You may be able to treat down to 200 micron. We have a new indication of keratoglobus, and we have integrated all of this into slit lamp crosslinking. Now, which brings me to the future. I would like to increase global access to this technology, which means we do not really need an expensive infrastructure anymore to perform crosslinking, especially not if you do epi-on. We should go to the most simple infrastructure we all have, which is the slit lamp. And this took us 8 years to develop. And this is a machine that you can use at the slit lamp in the upright position, as well as in the laying position. I use it very rarely in the laying position now. For example, here in a patient with Down's syndrome, intubation, general anesthesia. We've published the technique in the JRS, and we have checked a number of potential problems we have to overcome. First of all, gravity does not influence riboflavin saturation. This was a fear we had, that with gravity riboflavin will go down very quickly. It does not. You have 1 hour of time, and you only need a few minutes in crosslinking. Second, look at how stable the patients are during irradiation. This is a video. The patient is not moving at all. See, it's flickering. It's a video. Why? Look at the upper movie. We give the fixation light to the other eye, so the patient has a steady fixation point. Is the treatment uncomfortable? No. Please don't forget, we don't speak about 30 minutes at the slit lamp. We speak about 4 to 10 minutes with modern protocols. But most importantly, what about the infection risk if you do this at the slit lamp in an office setting? Well, in epi-on, we have no infection risk anymore. And even in epi-off, the infection risk is extremely small. I will publish 511 cases now that I've performed over the past 5 years without a single infection. And please remember, even intravitreal injections are moving to the doctor's office, to the examination room now. So if we can do IVTs, we can also do crosslinking. So these are just some impressions I can give you of slit lamp based crosslinking, which is available in more than 60 countries now. It works very nicely. Crosslinking has become a multifaceted technique, and I think that the future will be bilateral epi-on crosslinking at the slit lamp.